Hey, I'm Rob Witcher from Destination Certification, and I'm here to help you pass the CISSP exam. We're going to go through a review of the major topics related to cloud computing in Domain 3 to understand how they interrelate and to guide your studies. This is the 5th of 9 videos for Domain 3. I've included links to the other MindMap videos in the description below. These MindMap videos are one part of our complete CISSP masterclass. Cloud computing. Everybody and their dog is moving their infrastructure, applications, and data to the cloud, and innovating with emerging technologies like AI, blockchain, and IoT. Since March of 2006, when the first cloud service appeared, Amazon's simple storage service, good old S3 buckets, cloud has quickly become a massive part of most organizations' IT infrastructure, if not the dominant part. You would therefore expect that the CISSP exam would have a large percentage of questions dedicated to cloud, but that's not the case. You'll certainly see questions related to cloud security on the exam, but the reason there are relatively few questions related to cloud security, despite its importance to organizations, is because ISC² created a separate certification focused on cloud security, the CCSP, Certified Cloud Security Professional. Which, by the way, we also teach. So watch out for mind maps on that in the future. So let's go through some of the basics of cloud security you need to know for the CISSP exam. We'll begin with defining what is cloud computing. It's actually remarkably difficult to come up with a nice, simple definition of what is cloud computing, because cloud is many different things to many different people. It might be some servers you're running in your own data center that just have your data and you just have access to them. It might be someone else's application that you're just renting access to. It might be running a container somewhere or a federated identity management solution as a service. So how do we define what is cloud computing? A good method that the industry has come up with is to define a set of characteristics. If a service complies with these characteristics, then it's probably cloud. The first characteristic is on-demand self-service, which means users can request services and sophisticated software that the cloud service provider automatically provisions the services, usually within a matter of milliseconds or seconds. This is a huge shift from how things were done traditionally. It used to be, if you wanted to, say, have a new server provisioned in a large company, you'd have to submit a 17-page form to IT, and then it had to be approved in triplicate, and then you had to wait 4 to 6 months for the server to be set up. On-demand self-service means that basically anyone can request incredibly powerful services and have them provisioned near instantly. This is remarkably helpful if you want to innovate, experiment, and fail fast. The dark side, however, of on-demand self-service is shadow IT. The next characteristic is broad network access, which means access to cloud resources are available from multiple device types and from multiple locations. Basically, the primary way we access cloud services is through a web browser across a network. And everything has a web browser built into it and internet access nowadays. So you can essentially access cloud services from basically everywhere. The next defining characteristic is a really important one: resource pooling. There are 3 primary resources you need to do anything from a technology perspective. First, compute. The ability to fetch instructions, decode them, execute them, and store the results. Essentially the ability to execute code. Second resource is storage. You need to be able to store a bunch of bits somewhere, the data and the code. And the third resource is network. You need to be able to move a bunch of these bits around everywhere. These are the 3 primary resources you need to do anything in the cloud: compute, storage, and network. And a major defining characteristic of cloud is that these 3 primary resources are pooled and shared. As a user of cloud services, you typically don't have direct physical access to any of these resources. You're not directly accessing a CPU or directly accessing a hard drive or directly sending your traffic to a physical switch or a router. Instead, there's a layer of virtualization between the user and the resources. Or instead of accessing a physical hard drive, you're using a virtual disk or object storage. Or instead of accessing a physical switch, you're using a virtual switch. This layer of virtualization allows the resources of the cloud to be pooled, to be shared amongst multiple users much more effectively. Resource pooling is what makes it so easy to provision new services near instantly or rapidly increase or decrease your usage of compute, storage, and network. Which brings us to the 4th characteristic: rapid elasticity and scalability. You have the ability in the cloud to quickly provision and deprovision resources. If you need access to a bunch of additional bandwidth, no problem. You can rapidly gain access to vast amounts of additional bandwidth. Or if you need terabytes of additional storage, no problem. You can also just as easily deprovision, so you can rapidly increase and decrease your usage of cloud services. And the final characteristic is measured service, which means the cloud provider is closely monitoring your usage of the cloud, and you only pay for what you use. Resource usage is monitored and reported to the consumer, providing visibility and transparency of rates and costs. So that's the 5 characteristics of cloud computing. Let's now talk about the 3 most common cloud service models. Essentially the most common types of cloud computing. Infrastructure as a service is an environment where customers can deploy virtualized infrastructure, servers, appliances, storage, and networking components, basically allowing a customer to recreate an entire physical data center as virtualized components, virtual firewalls, virtual routers, virtual servers, and so forth. Platform as a service provides the services and functionality for customers to develop and deploy custom applications. Customers can create their own custom applications without having to worry about all the underlying complexity like servers and the network and storage. And software as a service is where a customer can rent access to an application hosted in the cloud. Those are the historical service models. We also need to talk about containers as a service and serverless, or more aptly called functions as a service. Containers and serverless are becoming increasingly popular and have a lot of developer momentum behind them. And there are now some basic questions on the exam about them, so we need to talk about how they fit in amongst infrastructure, platform, and software as a service. Containers as a service fits in roughly between infrastructure as a service and platform. And serverless fits in between platform as a service and software as a service. I'll talk in more detail about exactly what containers and serverless are shortly. For any flavor of cloud service, it is critically important to understand who is responsible for what. If there are no clearly defined responsibilities as to who is doing what, you can generally assume that no one is doing it. This diagram shows varying levels of who is responsible for what for the different service models. You absolutely do not need to memorize the specifics of what a customer is responsible for, the pink boxes, and what the cloud service provider is responsible for, the purple boxes. Just know this. Responsibilities must be clearly identified and assigned, and the onus for doing so is on the customer. The customer ultimately remains accountable for the protection of any data and services they outsource to the cloud. So the customer must ensure responsibilities are clearly defined in contracts and service level agreements, and the customer must ensure that the cloud service provider has controls in place which are operating effectively to meet the defined requirements. This assurance can be provided through service level reports or more commonly via SOC 2 reports, which I talk about in the first MindMap video for Domain 6, link in the description below. Now let's talk about the cloud deployment models. Public cloud is cloud services that are available to anyone, to the public. A cloud service provider owns and operates cloud infrastructure that is open for use by the general public. Private cloud, on the other hand, is cloud infrastructure provisioned for exclusive use by a single customer. Private clouds can be owned and operated by the customer or by a cloud service provider. And private clouds may exist on or off premise. And private clouds can be physically or logically separated from customers. It's complicated, but the simple definition, right, of private cloud is that it's reserved for one customer. Community cloud is cloud infrastructure that is only accessible by a small community of organizations that have similar shared concerns, similar security and regulatory requirements, for instance. And hybrid cloud is simply some combination of public, private, and community cloud. For instance, it is very common for large organizations to have their own dedicated on-premise private cloud for sensitive data, and they also use the public cloud for less sensitive data and workloads. Thus, they have a hybrid cloud deployment model. Next, let's dig into a little more detail on how you can access virtualized compute resources. As I mentioned as part of the resource pooling characteristic, you don't typically have direct physical access to a physical server or a physical CPU in the cloud. So how do you access compute? How do you run your code and applications? You have access to various types of virtualized computing options, and we'll talk about virtual machines, containers, and serverless now. Starting with virtual machines. A virtual machine is an operating system and some applications running on top of a layer of abstraction instead of running directly on the physical hardware. This is a good example of where a picture is probably worth 1,000 words. As you can see in this diagram here, at the bottom we have the compute node. This is essentially the physical server comprising a CPU, a bunch of RAM, a network interface card, etc. The physical hardware. In a traditional computer, the operating system would then be running directly on top of the hardware. But in a virtual machine, we have a layer of abstraction between the hardware and the operating system. What is providing this layer of abstraction? The hypervisor. The hypervisor is a piece of software. I like to think that the job of the hypervisor is to be a giant liar. Here's why. An operating system expects to have total and complete control of all the underlying hardware, because a key job of an operating system is to control all of the underlying hardware in a coordinated fashion. If we wanted to run 2 or more operating systems simultaneously on the same underlying hardware, it would never work, because each operating system would be trying to have total and complete control, and they would therefore conflict with each other. And yet we do this all the time by creating a layer of abstraction between the hardware and the operating system. The hypervisor, the giant liar. The hypervisor is simulating the underlying hardware to each OS. So each operating system thinks it is controlling the underlying hardware, but is in fact just controlling the virtual hardware that the hypervisor is simulating or emulating. This setup therefore allows us to run multiple operating systems and their applications simultaneously on one physical server, one compute node. And as you can see in the diagram here, we have 3 virtual machines. Watch out on the exam that virtual machines might also be referred to as instances or guests. And these virtual machines are running atop the hypervisor, which might also be referred to as a VM monitor. One little hint I'll add here related to hypervisors. Make sure you're familiar with the difference between type 1 hardware hypervisors and type 2 software hypervisors. Which is more security efficient? Type 1. All right, next let's talk about containers. Containers are highly portable code execution environments that run within an operating system, sharing and leveraging resources of that operating system. The basic idea here is that you can package your code inside a container, much like an intermodal shipping container. The cool thing about a shipping container is once you've stuffed whatever you want inside, you can now move that container around the world via ship, truck, train, whatever you want without having to repack the container. It's highly portable. Same idea with a container that you can put your code in. You stuff your code in the container, and then you can run that container on your Mac laptop or an on-premise Linux server, the Windows Azure cloud, the Google cloud. Containers make your code highly portable. Just like with virtual machines, there is a layer of abstraction that a container runs on top of. The difference is, where is this layer of abstraction located? With virtual machines, the abstraction is between the hardware and the operating system. With containers, the abstraction is between the operating system and the containers. This layer of abstraction is called the containerization engine. As you can see here, we can run multiple containers on top of the container engine. A big benefit of this is efficiency and portability. From a portability perspective, the container engine abstracts away the specifics of the underlying operating system. This allows the exactly the same container to run on a Windows server, a Mac, a Linux server, or whatever. The specific operating system doesn't matter, making containers highly portable. And the final type of virtualized compute we're going to talk about is serverless, or more correctly called functions as a service. Before we talk about serverless though, I think it's helpful to understand a fundamental concept about serverless. And that is, it's about separating an application into a bunch of interconnected functions. Take a look at this diagram here. A more historical way of developing an application is to create a monolithic application. This is where all of the functions of the application, all of the colored shapes, are packaged together into a large executable file. A disadvantage of this approach is that if the demands, the usage of the application grows, it can be difficult to scale the performance of the application. And often, only certain functions or groups of functions need to be scaled. Enter the next approach, microservices. The idea here is you take the same application, the same functionality, but you break the application down into groupings of functionality called microservices. One of the advantages of this is that it's now easier to scale the application, as you can focus on scaling whichever microservice you need to. Taking this decomposition a step further, we arrive at functions as a service. Again, the same application providing the same functionality, but we've broken the application down into individual functions. which talk to each other via API calls. This is a fundamental aspect of serverless. Simple functions are written and stored in the cloud, and these functions can be called as much or as little as desired. As a developer, you basically don't have to think about the infrastructure at all. If you want to call a function 1,000,000 times a second or once every 3 weeks, it is exactly the same function. And if you never call the function, you pay nothing. Zero usage equals zero costs. I'm obviously glossing over a huge amount of fascinating functionality here, but again, the CISSP exam is not a cloud exam, so the basic definition should be sufficient. Now, we're going to spend a fair bit of time talking about identification, authentication, and authorization in the cloud. The use of cloud basically destroys the last vestiges of the formerly pervasive practice organizations used to have of a well-defined perimeter and tightly controlling access to their internal trusted network. When an organization moves to the cloud, this concept of a trusted internal network essentially disappears. Identity is the new perimeter in the cloud. In the cloud, you should assume that all traffic is a potential threat. There is no trusted internal network anymore. Therefore, as security professionals, we must ensure that all traffic, all users are very thoroughly verified, so we know exactly who is accessing what. This approach is often referred to as the zero trust model for security, and it requires very robust identification, authentication, and authorization controls. So let's dig into these controls by first talking about where we can store users' identities. The two main places where we can store our users' identities are locally or in the cloud. Locally implies that some system, usually Active Directory, is being maintained by the organization on premise in the organization's own data center to store users' identities. And cloud obviously implies that a cloud service is being used to store an organization's users' identities. Okta is a good example of a cloud-based identity provider. Next, we have several options as to the types of identities that we can use. A cloud identity is an identity which is created and managed solely in the cloud. Linked identities are two separate identities, one in the cloud and one locally on premise. There is simply some indication of a linkage between them, but changes to one are not automatically synchronized to the other linked identity. Synced identities are very similar. You have two identities, one in the cloud and one locally on premise. The key difference here is that these two identities are synchronized. A change to one identity is automatically reflected, synchronized to the other identity. And federated identities. A user has one identity that allows them to gain access to both local and cloud-based services via federated access. This is the best way of doing this. I've already mentioned that it is incredibly important to have clearly defined accountabilities and responsibilities in the cloud. Let's define those terms. Accountability refers to an individual who has ultimate ownership, answerability, blameworthiness, and liability for an asset. They are the owner of the asset. Accountability should be assigned to only one person for each asset, because ultimately accountability means who is the throat that gets choked if something goes wrong. That is the accountable person. Accountability cannot be delegated. The accountable person can set the policies and requirements for protecting an asset and then delegate those responsibilities to others. Responsibility, therefore, means the doer, the person or multiple people that are in charge of the requirements that are defined by the accountable person. Multiple people can be responsible, and responsibilities can be delegated. Let's now talk about the various common roles in the cloud and their accountabilities and/or responsibilities. The cloud consumer is the customer, the person or the organization that is using the cloud services. Individuals within the cloud consumer will be the owners, also known as the data controllers of any data that is stored in the cloud. And very importantly, the owners, the data controllers, will be accountable for the protection of any data they store and process in the cloud. And remember, the owner cannot delegate their accountability. They remain accountable even if they outsource data to a cloud service provider. The cloud provider, also known as the processor, is of course the cloud service provider. The cloud provider will be responsible for protecting consumer data in the cloud based on the requirements set by the data owner. The cloud provider will also be accountable for running their own infrastructure and protecting their own data. Cloud brokers are middlemen. Cloud brokers are organizations that exist between the consumer and the cloud service provider, and brokers exist to do things like aggregation, arbitrage, and intermediation, essentially to package together various cloud services for a consumer or to add additional functionality to a cloud service provider's offering. And cloud auditors, rather obviously, are the people who no one likes because they show up to audit stuff and see if controls are properly designed and operating effectively. By the way, I'm allowed to say that because I have conducted a lot of cloud audits and no one likes me. There are various protocols that can be used to enable identification, authentication, and authorization in the cloud. Service Provisioning Markup Language, SPML, is an XML-based framework for exchanging provisioning information, setup, change, and revocation of access between cooperating organizations. Basically, SPML standardizes and simplifies the process for provisioning access across multiple systems in multiple organizations. The next three protocols all enable federated access. I talk about federated access in a lot more detail in the second video for Domain 5, link in the description below. SAML, the Security Assertion Markup Language, is a protocol that provides both authentication and authorization in federated access. OpenID provides only authentication, and OAuth provides only authorization capabilities. When an organization decides to move some of their systems and data to the cloud, there is a lot they need to think about from a security perspective. How do they ensure proper access controls, confidentiality, availability, and integrity of data, portability, interoperability, reversibility, resiliency, and compliance, among many other things? One way to tackle this problem is to take a data-centric view. Cloud consumers can focus on the data that they plan to migrate to the cloud, the classification of the data, and therefore the security controls that need to be in place for each stage of the data lifecycle: creation, storage, use, sharing, archiving, and destruction. One important contractual tool that a cloud consumer can use to communicate their requirements to a cloud service provider are SLAs, service level agreements. SLAs are documented commitments by the service provider to a consumer, covering things like confidentiality, integrity, availability, responsiveness, and so forth. And SLAs are addendums to the overall contract. Conducting forensic investigations in the cloud, especially the public cloud, introduces some significant challenges as well as opportunities. One of the primary sources of evidence when conducting an investigation in the cloud is obtaining a copy of a VM instance or snapshot. A VM snapshot is a copy of a VM that preserves the state and data of a virtual machine at a specific point in time. Very useful for investigations. Less useful would be the VM's volumes or virtual hard drives. There is obviously a lot of data stored on a hard drive from a forensics perspective, but none of the volatile data in the CPU's cache or registers or data in RAM that you can capture with a snapshot. And least useful from a forensics perspective would be a VM image. An image is a pre-built virtual machine. Looking at an image can be useful to help you identify vulnerabilities, misconfigurations, etc. But the image does not contain any of the data of the running system once it is instantiated from the image and running in production. All right, one final interesting challenge I will talk about related to cloud: defensible data destruction. Many laws and regulations around the world require a data owner to ensure sensitive data, particularly personal data, is defensibly, demonstratably destroyed. One possible method of defensively destroying data in the cloud is known as crypto shredding or crypto erase. The idea is that sensitive data is encrypted with an excellent algorithm like AES, and then every single copy of the encryption key must be physically destroyed. With no possibility of recovering the encryption key, the data has effectively been crypto shredded and is unrecoverable. Therefore, the data has been defensively destroyed. And that is an overview of cloud within Domain 3, covering the most critical concepts you need to know for the exam. If you're finding these mind maps helpful in your studies, you should check out the CISSP guidebook we wrote. It's called Destination CISSP, a concise guide. We wrote our guidebook to be as concise as possible, while still providing the details you need to know to confidently pass the CISSP exam. You can find more details on our guidebook and where to buy it here at DestCert.com/CISSP guide. Link is in the description below as well.